So design of compression member. The very first thing you required for this session is IS 800 2007 code. This is the steel code that you require for the steel design of member and structure both. Right. So this design of compression member is given in section 7 of IS 800 2007. So this is the code IS 800 2007. The name of the code is General Construction in Steel Code of Practice. So this code you will going to use for the steel design, and you can directly use the part of the code that is called compression member design. So this is section number 7, design of compression member. As I told in last session also, you must have hard copy of code or soft copy. So whenever I'm giving you the clause number or page number, at that time you also need to see in your hard copy or the section or the in soft copy. Right. So this section number 7 contains the design criteria for the steel column member. Now, column member, you are knowing that this column member is a vertical aligned member which will take the axial load, which may take the axial and bending, both the load. Right. So in analysis part, you have go through the uh, analysis of this column or the column and strut chapter in your syllabus, in your curriculum, where you have find out the critical load, P critical, that means load carried out by critical load carried out by the column. So by Euler's method or by ranking method. So the analysis part you are knowing that these are the analysis of the column. Now in design, what are the criteria that you need to keep in mind for the safer design of the column that we are going to see in this particular section number 7. So this is section number 7. So before starting with this section number 7, the very first thing that you need to understand, or you are knowing, that the effective length of steel compression member. So this part is already known to you that for the different support condition of the column or different support condition of column. So say for example, I am drawing the line diagram for the column. So if this is my vertical column, and if this vertical column is supported by both the side fixed support, these are the two fixed support at both the end, then what could be the effective length of the column to be considered for the analysis and for the design. So this slide you have studied, you have used in your analysis part also, and in design, and you will use in design part also. Say for example, if any other column member or the vertical member is fixed and free at the other end. So this type of column deflection behavior also you are having that knowledge, that how this kind of beam deflect, and due to that deflection, how the effective length is to be considered for the analysis and design. So I'm just showing
Grammarly
you.
is your personal writing assistant for clear
Are you
emails,
able
confident
to
messages,
hear
stronger
the
essays, and more.
voice of this YouTube?
Which column is most
Yes,
like
ma'am.
buckle? A pin connection on both ends, and this little signal here means it's a pin connection. So you can picture it like a rod being held between your fingers. That's a pin connection. You can kind of pivot. A moment connection.
So this YouTube video is showing the different support condition of the column member or the vertical member, and due to that support condition, how the vertical member deflect, and the meaning of this pin connection, moment free connection or fixed connection in the actual site, on the actual condition in steel member, that you will see in this video. So just concentrate on the video. This is only 7-minute video, but some of the things you have studied and some new things you will learn.
On one end and free or no connection on the top. A moment connection on both ends, and a moment connection would be more like a rod being held in your fist.
Also, column is known as axial member. Generally, the vertical load are passing from the column, and somewhere the connected beam moment is also transferred to the column member. So, column member is also known as axially loaded member, or the member which is having the axial load.
Go ahead and hit pause. The answer is this one, the moment connection on one end and free no connection on the other. So this is a little bit counterintuitive, but there are different ways to brace a column. And we have pin connections, we have moment connections, we have free connections, which are a little bit more unusual, and we have ones that are allowed to translate right to left, and we'll get to those. So if a column is going to buckle, we need to figure out not only the strength of the column and the length of the column.
So here buckling means when applying the axial load on the column, as the member is vertical member, it will start buckling, right? And that is called the buckling. If you have the flexure member or the beam member or the horizontal member, then by applying the load on the horizontal member, the beam start bending. So there is difference between bending and buckling. Bending will occur in the horizontal member, in the beam member, and in bending the load is perpendicular to the member, but in buckling the load is parallel to the member.
But the type of connection at the top and the bottom is going to kind of govern its likelihood of buckling. Now we're looking at a table, and here you have just different flavors of column. So in A, you have fixed up, top, and bottom. On B, you have a pin connection at the top and fixed at the bottom. On C, you have something that's a rotation fixed but translation free on the top, and something that's rotation and translation fixed on the bottom. On D, we have two pin connections. On E, you have something that's fixed on the bottom and allowed to kind of move around at the top. And then on F, we have something that has a pin connection on the bottom and translation on the top. Now,
Is it clear to you how the vertical member buckle due to axial load with respect to different variation in the support condition? Is it clear?
Yes, ma'am.
This thing you have studied in your column and strut analysis part. But this is the repetition. Why? Because this required in our design also. That's why this is very important thing to understand.
what we're going to need to do when we do the calculation, when we kind of figure out likelihood of buckling, we're going to have to run through a formula. And I'm not going to get into the formula right here, but in that formula, there's a value of what's called K. And that K value, you look up on this table to determine its likelihood of buckling. And a higher K value means a higher likelihood of buckling, because in the formula, you're going to take the length of the column and you're going to multiply it by K. So in this one right here, we're going to take the length of the column and we're going to multiply it by 1/2. We're going to multiply it by 0.5. That means from a buckling point of view, this column of, say, 10 feet will behave more like a column that's only 5 feet. If we look at this one here, if we have a column that's fixed on the bottom and it has a pin connection on the top and it's 10 feet long, in terms of its likelihood of buckling, we're going to multiply it by 0.7, so a 10-foot column will look more like a 7-foot column when we size it for buckling. And then this is kind of our baseline. We have pin connections at the top and the bottom, which means that it's rotation free and translation fixed. And that's our one. So then if we have a 10-foot column, it's going to really behave like a 10-foot column. But look at these two here. These two have a theoretical K value of 2, which means that we're going to have to take a 10-foot column if we have one of these, and it's going to behave like a 20-foot column. So we're going to multiply it by 2. Now, right below that theoretical K value, there's another line that says recommended design value when ideal conditions are approximated. And that basically means we're talking about wood. So the theoretical K value can pretty much work if we're talking about something like steel that's pretty consistent, maybe even concrete that's pretty consistent, but wood is kind of weird. It's got knots and it's got wanes and checks and cups, and no piece of wood is perfect. No two are the same. So in this case, we're actually in some of these situations, we're going to have a slightly larger recommended K value for wood. So let's go through examples of what we mean by rotation fixed and translation fixed and so forth. So this is a moment connection. We saw this before when we talked about steel. It's a moment connection because we've engaged the flange and the web, and we're holding both of them in place. And so that would be a rotation would control, but yes, same principle. It's a knots, and we're actually fixed and translation fixed and so forth. So this is a moment connection. We saw this before when we talked about steel. It's a moment connection because we've engaged the flange and the web, and we're holding both of them in place.
Okay, so this is called the moment connection. Fixed support. Fixed support means there is no translation, no rotation, right? And for no translation, no rotation in the connection, in the steel connection, this angle, cleat angles are connected with your member. This is called the beam member. This one is the beam member. This vertical is the column member, and beam and column member together are joined with this angle, cleat angle. Right, so there is no movement in translation, no movement in rotation.
Place. And so that would be a rotation, and we're holding flange. We saw this before when we talked about steel. So this is a moment connection. We saw this before when we talked about steel. It's a moment connection because we've engaged the flange and the web, and we're holding both of them in place. And so that would be a rotation fixed and translation fixed. It's not going to slide up and down. It's not going to rotate. This is what we called a shear connection before. This one is what we would, in the language of that chart we just looked at, that table we just looked at, we would call this rotation free and translation fixed. It's not able to slide up and down, but even though there are 3 bolts there, it is actually able to kind of pivot because at the scale of the building, those 3 bolts are really kind of like a pin. Then we have rotation fixed and translation free. Go ahead and hit pause and try to determine where we use that kind of connection. It's in seismic. So remember we talked about buildings kind of sliding back and forth. And you'll note that we talked about structures in all kinds of other places, right? We talked about it certainly in steel, but in other places as well. So these are the seismic isolations that are in this case, under the Utah State Capitol. If we want something to be able to slide back and forth, that's going to be something we're going to call rotation fixed and translation free. So it can't pivot, but it can translate right to left. Finally, we have our rotation free and translation free. And certainly, of course, a flagpole comes to mind. What kind of works with this at this level? It's kind of rare, and it's not very common in buildings. We sometimes will see it if we have like a single column for a highway overpass. That may behave like something that is rotation free and translation free. Now, I just gave a in-person seminar at AIA New York.
Right, so this was regarding the effective length of the compression member, and this you can see, this table you can see from table number 11 in IS 800. So this is IS 800, and in table number 11, this is the table. Right, all the supports are given, different varieties of support conditions are given, This is table number 11, right? So if you are designing any column, then you first need to see that which are the support conditions are given at the two end, and depend on that only you can consider the length of the column, right? So the different boundary condition at one end and at other end is given. You can see over here translation restraint, and here translation free. Restraint means you are not allowing, free means you are allowing, and for that the schematic representation in terms of the deflection behavior of the column or the vertical member is given, and for that condition the effective length is given, right? So you can consider for your design you require to know the length of the member, and that you can find from this table number 11. Clear? This table 7.2.2.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Now coming to the typical compression members in form of sections that you are using. So before showing this slide, let me show you slide so that it can be easy for you to understand. So these are the typical section that we are using for the column member. See this bottom part, this bottom figure where my cursor is moving, this is the column member. The vertical member is the column member. This column, if you need to design, then we need to give the section, steel section we required to give, right? So which shape of the section, steel section you are designing, that is depend on the designer, and the available section for the column members are the very first, this is I-beam section, I-beam, this is the steel I-beam, right? This is called the flange. Uh, this is called the flange member. And this is called the web member, right? So this from the I section. This is called the channel section. This is the channel section, right? This is called the angle section. Angle. This is called the angle section. This is called the flange section or T section, right? This is called the wide flange. The width of the flange is larger than this I beam, this beam. That's why it is called the wide flange. But it is I section, but having the wider flange. Right. This is called the hollow steel section. This is called the hollow. This is the hollow section, steel section. Right. So these different varieties of section you can choose as per your loading condition, as per your support condition. Right. So here is the one of the column. See this over here. This look like a T section. अगर इसका top view देखोगे, then you can realize that this is T section. From the top view, you can see the T section. Right. See over here. This is T section. This is T section. Somewhere C sections are also provided, and somewhere some built-up sections are also there. Now here you can see this is the solid steel section. This is the hollow section, circular section. This is the hollow square section. Now this is I section. This is I section. This from the I. And on that one plate, steel plate is provided. So this type of section is also there for the column member or compression member. If the load is very high, if only I section is not sufficient, then after you can provide one plate also above the flange, above and below the flange like this. So this is I section with plates on flanges. Then this way also the arrangement can be done. Double I section, two I section with single plate. Then channel section. As I told you, this is the channel section. This is called the channel section. This is called the channel section. And to form the column, channels are placed like this, back to back, channel back to back connection, right? With battening, like plate. This is the battening. Right, this is I section with white plates and flanges. White plate means the width of the plate is higher than the flange width. Right. Then this is called the angle section. Two angle section connected with the lacing like this. Some simple angle section are also used. This kind of arrangement can also used. Then this is called the built-up section. Built-up section means you are making a combination of steel section together. That is called the built-up section. So here I section and two channel section is making the built-up section. Right? This is called the I section. Right. So these all are the built-up sections. See, this is channel, two channel section. This is channel. This is channel. This solid line is the plate and this dotted line is the metal. Here the channels are placed back to back. This is the back side of channel. This is called the back side. So channels are placed back to back with metals. This is also channel section. Two channel section back to back. Steel plate above and the metal. Then channel, I section and top and bottom plates. This is called the built-up I section. You can make your own dimension for the I section, and this is built-up box section. Means the angle section or channel section are making some box type of section. Right. So these are the typical compression member that we are going to use for the steel column design. So you must have in your introductory part of Nirpek sir and Ankit sir session, you must have seen that the steel member or the steel sections are hot roll section, it is called as hot roll type of sections, hot roll sections and cold form sections. Right. So this all are the hot roll sections. So this rolled steel beam section is called the beam section, I section. And these are the some designation physical property section. This we will see in SP6 or the steel table. This is the channel section. This is the channel section. This is called the flange part. This is the width part. Width of the flange is denoted as BF. B means width and F for flange. And width of the web, this is called the web. I section में ये web है. So web को आप thickness of web को आप लिखोगे T into W, TW, thickness of flange. This is TF, thickness of flange. Right, this is called the angle section. This is called the angle section. See, moment of inertia or this channel section is considered to be the unsymmetrical section because the CG of the section is passing away from the center. So here also this is called the unsymmetrical section. This one is also unsymmetrical section. This all section CG value you have studied in strength of material. So that also we will use in the design part. that what is moment of inertia Ixx and Iyy of any steel section. This also you need to find out. And you have studied radius of gyration, right? So that all part we will see in the design also. So whatever you have studied in past, that won't uh, you know think that you can easily forget, because the application of all that subject will be there in your design chapter. So this is the now coming to as this is the common section that you can use, right? This is called the effective length. Now for design of any member, I used to say before the design of any member, you must aware about the failure criteria. You must aware about the failure criteria, how the member fail, and then you can make the safer design. So here also you must learn, you must aware about the failure type of the failures in the steel compression member, how the steel compression member fail. That knowledge you must have, then and then you can make, you can understand the safer design of the steel member. So basically this steel member or steel compression member fail in these three criteria, in these three types. One is known as the failure due to buckling. One is known as the failure due to buckling. Second is failure due to torsional buckling. What is difference between buckling, torsional buckling? We will see in this video. So first is due to buckling, torsional buckling, and third is known as the local buckling. Right, third is known as the local buckling. First we will see all these three videos, then after we will discuss all these figures, then we can easily understand the difference between buckling and torsional buckling, and difference between buckling and the local buckling. Right, so I'm playing this video.
This video shows a pin-ended column of load.
The voice is clear?
Yes, ma'am.
Slenderness being tested in compression. This type of specimen is commonly referred to as a stocky column. The specimen is a rectangular hollow section made of structural steel. The length has been chosen such that the failure is dominated by the material strength. The loading diagram shows a purely axial compressive force evenly applied to both ends of the specimen. The testing rig is now starting to apply a compressive force to the specimen. We can see the top end displacing and the column begins to deflect sideways as a result of the material damage, which can be seen at midspan on the concave side. Once this occurs, the column begins to lose its load carrying capacity. This particular phenomenon is not in the elastic but in the plastic range. Therefore, the failure is governed by the material rather than the geometry of the specimen. Turning the specimen to the side, you can see that the deformation has localized to the midspan of the specimen in a plastic hinge. The graph initially shows a linear relationship between force and displacement. In this range, no sideways displacement has taken place. However, once failure takes hold, the slope begins to reduce rapidly, and the point at which the curve becomes flat marks the failure load. This video shows a pin-ended column of intermediate slenderness being tested in compression. The specimen is a rectangular hollow section made from structural steel. The length has been chosen such that there is an interaction between the failure of the material and failure by buckling instability. The loading diagram shows a purely axial compressive force evenly applied to both ends of the specimen. testing rig is now starting to apply a compressive force to the specimen. We can see the top end displacing and the column begins to deflect sideways as a result of structural instability, which is better known as buckling. The shape of the column is theoretically a half sine wave. However, as loading progressive, this shape distorts as material damage takes hold. The deformation begins to localize at midspan. Once this occurs, the column begins to lose its load carrying capacity and failure ensues. This particular phenomenon starts in the elastic range, but the structural failure is due to a combination of geometric and material effects. Turning the specimen to the side, you can see that the deformation has localized to the midspan of the specimen in a plastic hinge. At the beginning, the graph shows a linear relationship between force and displacement. In this range, no sideways displacement has occurred. When this graph reaches a peak, however, this is the point at which buckling and material failure are effectively triggered simultaneously, and an initially sharp reduction in the load carrying capacity is seen. This video shows a slender fixed-ended column being tested in compression. The specimen is a rectangular hollow section made from structural steel. The length has been chosen so that the failure is dominated by a buckling instability. This is primarily a geometric effect. The loading diagram shows a compressive force evenly applied to both ends of the specimen. The testing rig is now starting to apply a compressive force to the specimen. We can see the top end displacing and the column begins to deflect sideways as a result of a structural instability, which is better known as buckling. The profile of the column as it buckles is theoretically a full cosine wave. Note that the column ends do not rotate due to the fixed-ended conditions. The column maintains this shape as it continues to deflect, until eventually material damage takes hold, which distorts the shape. And material effects are secondary, but ultimately trigger failure. The graph initially shows a linear relationship between force and displacement. Up to this point, the column hasn't begun to displace sideways. Once the buckling instability is triggered, however, the slope effectively reduces to zero. Finally, after significant displacement, the load carrying capacity begins to reduce, and this marks failure from material effects.
So these three are the video for the buckling, where due to support the column is getting buckled, right? So that is called the simple buckling of the column member due to support condition. Now the next video is for the torsional buckling. Now in spite of only buckling, now your members start rotating, and that buckling is known as the torsional buckling. Here in this first three video, due to fixity at the support, only due to that support the column get buckled, right? Only the buckling or the deflection is taking place, but whereas in this condition not only translation but rotational movement will be also there in the column.
Okay, we have two angles here. The difference between these two is the leg size. One is twice the size of the other, so you would think that the larger one should carry more load. But the theory we have seen previously indicates that this should carry less load, and we'll demonstrate it. As a matter of fact, of these two loads, this member is going to buckle at the smaller one. So you can see that the section has twisted in a torsional buckling mode. And this is what's known as torsional buckling. Now I'm going to put in the smaller member. I'll put on the same load. And it carries it with no problem. It's going to take a larger load to buckle this member. So larger does not mean stronger.
So here in this last video, you can easily see the buckling is taking place in with respect to twisting. So here in this case, here this is the twisting and buckling together. Your member twist also and bend also, buckle also, right? This is called the simple buckling, flexure buckling, or lateral buckling, not flexure, lateral buckling. So here, if this is your I section, this is your I section, you are aware that for I section there are two axes are there. One is called the major axis and one is called the minor axis, right? Major axis means where the moment of inertia is more. So if this is I section, if this is symmetrical section, I section, then what will be the major axis, IXX or IYY? For I section, which will be the major axis, IXX or IYY?
IXX.
IXX. So IXX is more, IYY is less. So here in this case, you are applying the load. Due to this application of load, the buckling is also, the behavior of the buckling with respect to major axis and with respect to minor axis is different. So if you are applying the axial load over here on the I section, if this is major axis, so the buckling or the deflection of the major axis is somewhat lesser than the minor axis. So here you can see the deformation of major and minor lateral buckling. And this is the buckling with the torsion. Buckling with the torsion. Right. Now coming to this local buckling. This is called the lateral buckling. Right. Now coming to local buckling. Now what is this local buckling? See, by providing any I section that we have discussed over here, this is the I section. Now sometime what happen, if you have chosen the wrong cross section for the applying load, what will happen before applying the load, or at least at the initial load only, if the section strength is not enough, then the section may fail into flange or in web. The section may fail into flange means if this is the I section, then I section may fail like this in this case, or your web also buckle like this, right? This portion, right? So this is called the local buckling. So section don't fail. Section will not fail, but the flange or web, one of the part will fail, and that is called the local buckling. So see over here, this is your I section, and this is called the local buckling. The buckling or the failure is observed at the flange part only. Here also you can see this part is buckle only, not the whole section. पूरा section fail नहीं होता है, पूरा section buckle नहीं होता है. Only part of the section is buckled, right? And that is called the local buckling. Here also you can see this is the steel member, so यहाँ पे ये buckle हुआ. right? So that is called the local buckling. So whole member will not buckle, but the part, flange or web can buckle. Is it clear? Clear the concept of buckling, torsional buckling and
Yes, ma'am.
local buckling?
Yes, ma'am.
Okay. So with this much of knowledge, at least we can start with the design example, and by the time whenever it is needed, we will go through the section 7 for the criteria purpose. So all of you just write this data, design a column using an I section. Okay, before that I would like to show you the steel table. This is called the steel table. This is not the steel table, this is SP6. This is called the SP6 Handbook of Structural Engineer, Structural Steel Section. This is the handbook for the Structural Steel Section, SP6. So here you can see the different steel sections available in market, and from this handbook only or from the steel table you can choose your section for the design purpose, right? So here if you can see over here, this is start with the table number 1, that is rolled steel beam. This is I section, rolled steel beam, as I have shown you the I section, right? So the property of this I section with different designation is given over here. Now do you know what is the full form of all this designation? I member, anywhere in class if you have heard, आपको बताया है स्टील के लेक्चर में? Quickly, yes or no?
No, ma'am.
Okay. So the meaning, this is I section, ये I section है, ठीक है? तो different I sections are there और उसको designation दिया है. This is the designation or the name of the I section. ISJB. You can write in your notebook. The full form of ISJB is Indian Standard. I for Indian, S for Standard. Indian Standard Junior Beam. Indian Standard Junior Beam. Right. This is the name of this section. Here this 150, ISJB 150. So this 150 represent the depth of the section. मतलब ये जो height है, ये जो I section है पूरा उसका जो height है, this height is represent with the number. So this is 150. So ये कैसा होगा section? ये अभी मैंने आपको आगे बताया था. This is the full section view. ये ऐसा यहाँ पे, ठीक है? तो ये है पे पूरा आई सेक्शन, आपका आई सेक्शन. ये है आपका व्यू, आई सेक्शन का व्यू. तो जो हाइट होगी, दिस हाइट रिप्रेजेंट दिस नंबर 150. सो ISJB मींस इंडियन स्टैंडर्ड जूनियर बीम 150. राइट. हियर द सेकंड कॉलम इज वेट पर मिनट. मतलब कि ये जो आई सेक्शन है 150 हाइट वाला, उसका वेट क्या होगा? स्टील सेक्शन है, उसका वेट क्या होगा? व्हाट इज डेंसिटी ऑफ स्टील? चलो फटाफट, व्हाट इज डेंसिटी ऑफ स्टील?
7880.
7850 यूनिट kg per meter cube. Right. So this is density of steel. So if you required weight per meter, तो आपको क्या करना है? डेंसिटी इंटू एरिया ऑफ सेक्शन मल्टीप्लाई करो, देन यू विल गेट इन kg पर मीटर, वेट पर मीटर. तो वो जो वेट पर मीटर है वो है ये 7.1 ओवर ये सेक्शन का. राइट. यहाँ पे उसका सेक्शनल एरिया दिया है, आई सेक्शन का एरिया फाइंड किया है, एरिया ऑफ आई सेक्शन. दिस ऑल थिंग यू हैव स्टडीड इन स्ट्रेंथ ऑफ मटेरियल. दिस इज कॉल्ड द डेप्थ ऑफ द सेक्शन 150. दिस इज कॉल्ड विड्थ ऑफ द फ्लेंज, BF. विड्थ ऑफ द फ्लेंज को अगर लिखना है दैट इज BF, विड्थ ऑफ द फ्लेंज BF. तो ये है विड्थ ऑफ द फ्लेंज, यहाँ से यहाँ तक का डिस्टेंस। देन थिकनेस ऑफ द फ्लेंज TF, थिकनेस ऑफ द फ्लेंज यहाँ से लेके यहाँ तक की जो थिकनेस होती है वो। थिकनेस ऑफ द वेव, तो ये है आपका वेव, दिस इज कॉल्ड द वेव। तो वेव का यहाँ से यहाँ तक का जो थिकनेस होगा वो, ठीक है। नाउ हियर यू कैन सी मोमेंट ऑफ इनर्शिया। नाउ दिस यू हैव स्टडीड इन strength of material, how to find moment of inertia Ixx Iyy for the I section. आपको this you have been given with height, thickness, then width, you can easily find Ixx and Iyy. तो ये यहाँ पे directly दिया हुआ है, right? But the application, this is the application and you have studied in strength of material. Also you have studied radius of gyration, how to find radius of gyration. So that also is directly given to you in this table, right? So for any of the section, this all parameter will be given to you. Parameter will be available in steel table or in SP6, right? So this IS, quickly write down, ISJB is Indian Standard Junior Beam. Here it is mentioned ISLB. So Indian Standard, IS stands for Indian Standard Low Weight Beam, low weight beam. Beam, right? ISLB low weight. ISMB Indian Standard medium weight beam, right? So this way you can get this, and not only this are the parameters for this section. The continue part you can see over here, modulus of section. आया था आपको स्ट्रेंथ ऑफ मटेरियल में Z वैल्यू मॉड्यूलस ऑफ सेक्शन की, है ना? हाँ, so this all things are given in this table, right? So then ISWB, this ISWB means Indian Standard Wide Flange Beam, medium standard wide flange beam. So these are the name of the I section, different I section. फिर टेबल 2 में आपको मिलेगा चैनल सेक्शन, टेबल 2 इज हैविंग द चैनल सेक्शन, बराबर? तो ये पूरा चैनल सेक्शन की प्रॉपर्टी। फिर आपको टेबल 3 में मिलेगा इक्वल एंगल सेक्शन। इक्वल एंगल सेक्शन मतलब क्या हुआ कि अगर ये आपका एंगल सेक्शन है तो ये डायमेंशन और ये डायमेंशन दोनों सेम हो, उसको बोलते हैं इक्वल एंगल। सो उसका भी आपको ISA डेजिग्नेशन है। ISA का मतलब इंडियन स्टैंडर्ड एंगल 20/20, 20/20 मीन्स दिस इज ऑल्सो 20, दिस इज ऑल्सो 20, सो 20/20। फिर थिकनेस दिया है तो थिकनेस मतलब ये थिकनेस दिया है, ये थिकनेस दिया है, ठीक है। ऑल अदर प्रॉपर्टीज आर गिवन। सो दिस इज इक्वल एंगल, दिस इज ऑल्सो इक्वल एंगल, this is unequal angle. Unequal angle means ये dimension and this dimension both are different, ठीक है? Unequal section पूरा। Then this is called the bulb angles. This is different than the angle section. यहाँ पे ये extension part है, that's why it is called the bulb angle. So these are the different type. This is the flange section or the T beam section, T section, right? This is the property for the plates. अगर आप I beam के ऊपर plates डालते हो तो plate का जो भी dimension चाहिए you will get from this table. Likewise, this is SP6 or you can use steel table also, and you can get the property of steel section that you are using for the design purpose. Different भी है, यहाँ पे देखो I section with joints, plates, additional plate. तो ये सबका प्रॉपर्टी है। बाय द टाइम डिपेंड ऑन द चूज ऑफ सेक्शन सिलेक्शन यू कैन यूज दिस SP6 in any of the chapter, right? So I think time is over, so we will continue this design example in next session. Till then, if you have any doubt, you can ask.